So welcome to the first slot of the IMG session. We will start with the presentations that we have scheduled. Let me check the title. So the first one is, I think it's Felix who is going to give it. Is right, Felix, are you there?
I am there, but my colleague Gareth Randall will present.
Yeah. Okay, Gareth. Okay, so the presentation is called Influence of Audiovisual Realism on Communication Behavior in Group-to-Group Telepresence. So Gareth Randall, I think from Bauhaus University at Weimar, will present it. Please go ahead. You can share your screen if you want.
Okay, right. I get the message saying you cannot start screen while the other participant is sharing. So I suppose, yeah, okay, I'll try again now.
Right. Can you try again, please?
Yeah, okay, that looks right. And it should be this one. Okay.
Yeah, now it's working. Go ahead.
Great. So yes, good morning, good afternoon, or good evening. My name's Gareth Rendell. I'm from Bauhaus University Weimar. Yeah, I'm happy to be able to introduce our work investigating the influence of audiovisual realism on communication behavior in group-to-group telepresence. This was a joint project between Bauhaus University Weimar and TU Ilmenau. And as you can see, we already presented this at the IEEE VR conference in March. But in this version of the talk, I'll try to go into a bit more detail about the evaluation methods that we used in the study. So yeah, telepresence systems bring geographically separated users together in a shared virtual space where remote users are represented by expressive life-size avatars. And group-to-group telepresence systems support communication between multiple remote parties. Such systems, like the one shown here, based on a multi-user stereoscopic projection screen, allows users to communicate simultaneously with co-located and remote conversation partners, meaning that the virtual representations of remote users can be directly compared against a real reference, i.e. the co-located users in the room. And the three research questions addressed in this work relate to this characteristic of group-to-group telepresence. The first one addresses the impact of the realism of remote users' avatars. Previous works have compared reconstructed avatars, which are generated in real time from image streams, with tracked CG avatars, which are pre-generated and then animated during runtime by the tracked movements of the user, but all in one-to-one telepresence scenarios. And they found that reconstructed avatars lead to more social presence, more trustworthy interactions, and higher positive affinity. In this work, we ascertain if this holds when avatars can be compared with real users, as well as investigating how avatar realism affects communication quality in a group-to-group scenario. The second research question investigates the impact of spatial audio, which has shown benefits in video conferencing systems and immersive listening scenarios, but not yet in immersive communication scenarios. So my co-authors and I have performed various experiments in immersive communication scenarios and have not yet observed an effect of spatial audio on behavioral measures or more holistic measures of communication quality like social presence. And here we investigate whether this more complex listening scenario with multiple virtual and real sound sources results in a measurable impact of spatial audio on communication. The third research question asks how communication between co-located users differs from communication between remote users. The group-to-group context supports this comparison because users interact with co-located and remote users simultaneously. So to answer these questions, we designed a group-to-group telepresence study. 16 groups of 4 participants completed the study, with the groups of 4 split between 2 locations. Yeah, and a multi-user projection screen in each location allows the groups to communicate in a shared virtual space. So we can see the participant point of view on the right, they all see two remote virtual users and one co-located real user. The study had a within-subject design with two independent variables being manipulated. Firstly, the avatar realism was varied between two levels, with remote users being represented as real-time reconstructed volumetric avatars in one mode, and abstract avatars with very simple geometry animated by tracked movements in the other mode. The second independent variable is the oral spatial realism, with the remote user's voices being spatialized in one mode and presented as a diotic signal that is the same in both ears for the other mode. And these variables resulted in 4 different study conditions, which were counterbalanced throughout the study. The participants therefore performed 4 trials, each corresponding to one condition, and in each one they performed a conversation task, specifically the survival task. They were given a description of a survival scenario and a list of 3 items on a piece of paper. And their task was to discuss and agree on 6 of the, in total, 12 items that would be most likely to help them survive in the given scenario. So the number of items was adapted slightly from the recommendation to prevent the task from taking too long. And we adjusted a few of the item names for better understanding, for example, converting to metric units. And yeah, the task was completed in the allotted time of 8 minutes in 57 out of the 64 trials. And the mean time of the completed task was 5.5 minutes. We chose this task because it fosters a more natural discussion than some more structured tasks. And every participant has to contribute something because of the distribution of the items. And in general, the feedback from participants was quite good, and people did seem to enjoy the task and remain engaged throughout. Participants completed a 26-item questionnaire after each trial. For better reliability, we analyzed the responses in a combinatorial manner by forming item groups corresponding to various aspects of communication. 2 of the item groups were taken directly from the Network Minds questionnaire, and they assessed whether participants felt that they understood and were understood by co-located and remote teammates respectively. Another item group assessed perceptions of the remote user's visual avatar quality, and another item group related to the overall group cohesion. We recorded participants' movements and voice signals with the Immersive Study Analyzer, which my co-author Anton Lemmert will speak about in the next presentation. And to obtain behavioral measures relating to communication, we analyzed head orientation data as a proxy for gaze with an approach that was inspired by Otsuka's 2018 paper. This allowed calculation of the gaze likelihood, which is the proportion of time a participant was looking at the co-located teammate, the remote teammate opposite them, or the remote teammate that was adjacent to them. And we also classified and quantified glances as unbroken periods of visual attention paid to the same target. So we can have a look at the results now. And first, let's see how avatar realism impacted the questionnaire responses. Again, we're analyzing the score distribution of the questionnaire item groups rather than individual questions. And despite the visual artifacts, which in the reconstruction of the volumetric avatars, which were partially caused by the shutter glasses that everyone has to wear to use the stereoscopic projection screen, we found a significant positive effect of the more realistic volumetric avatar condition on perceived message understanding, the rating of visual quality of remote users' avatars, and the perceived cohesion of communication within the group. Analysis of the gaze data shows that participants spent significantly more time looking at remote teammates when they were represented as volumetric avatars. And volumetric avatars were also associated with a higher glance frequency at remote adjacent teammates. So we found that the visually more realistic volumetric avatars have a positive impact on subjective communication measures. And the increase in visual attention found through gaze analysis, at least when considered in the context of these positive effects on subjective measures, also suggests that users are more engaged or were more engaged with when interacting with realistic avatars. And we therefore conclude that even though the imperfect appearance of the realistic avatars can be directly compared to real stimuli, visual realism is still beneficial in this group-to-group scenario. The second research question addressed the impact of spatial audio, and here we found no significant effect, again, on the audio condition, on the responses to the questionnaire, and only minor differences through gaze analysis. This was quite surprising since we expected spatial audio to help identify the speaker after a speaker change, especially when the facial expressions were not shown. However, it may be that the spatial cues were effectively redundant in this study because speakers could have been differentiated by their different voices, and also fast and precise sound source localization was just not specifically required to solve this particular task. Yeah, our third research question investigated how co-located communication differs from remote communication. And we can here directly compare the ratings of message understanding, which participants gave relating to co-located and remote teammates respectively. And here we can find that participants felt that it was slightly easier to get their message across to co-located participants than remote participants overall. And when we break this down by the type of avatar which they were interacting with, we can see that the difference between ratings for co-located and remote communication is larger when the abstract avatars were used, and when the volumetric, more realistic avatars were used, the difference between co-located and remote perceived message understanding was smaller. We can also analyze the gaze interaction and how it differs between co-located and remote pairs. In this case, since participants were most likely to look at the remote opposite participant in blue, just due to the positioning of the participants, it's more instructive to compare the gaze behavior relating to the co-located and remote teammates in green and yellow, respectively. And here we can observe a non-significant tendency to look at the remote adjacent teammate more often. And the glance frequency, number of glances per minute, also shows that more glances per minute were paid to the remote adjacent teammate rather than the co-located teammate. So yeah, it's unsurprising that we found that participants rated the unmediated communication to be better than that with remote teammates. The finding that there are more glances paid to remote participants is a bit more difficult to interpret because it's unclear whether the glances indicate engagement here or rather reflect increased difficulty maybe in interpreting these nonverbal communication cues from avatars, which wouldn't have been a problem so much with co-located teammates. Either way, I think this highlights the difficulty of interpreting these automatically detected behavioral measures without considering the context through manual coding. So to summarize, we conducted a group-to-group telepresence study assessing the effect of avatar realism and spatial audio on communication through questionnaires and behavioral analysis. And while spatial audio had few effects on the measures of communication quality, visual avatar realism improved understanding and group cohesion. In future work, we aim to investigate HMD-based group-to-group telepresence. In those scenarios, spatial audio may play a more important role since participants can move around the scene more freely. They're not stuck to this screen, basically, and they may therefore move outside of other users' field of view, meaning that spatial audio cues are more useful. And also when using devices like the Quest 3, co-located users may only be visible through video see-through displays, which slightly blurs the lines between real and virtual stimuli, because we see a kind of a slightly pixelated version of the real people. And we are interested in how this affects the subjective ratings and the behavioral differences between remote and co-located communication that we observed in this study. So yeah, that was it from me. Thank you very much for your attention, and I look forward to answering any of your questions.
Thank you, Gareth, for the presentation. Questions? Also, just to remind people online, you can just raise your hand in the Zoom link and we will take your questions too. Narciso.
Thank you for your presentation, Gareth. According to your results, the two people who are, let me say, to the right or to the left of the person who is conducting the analysis, give more or less the same results in all the cases. That is totally different than the other one. I expected that the person collocated should be clearly better in any kind of analysis, should give better results than the person who is remote adjacent. Have you any guess about the result that, let me say, in a overall view of your problem, my understanding of your presentation is that either the collocated and the remote adjacent gives in some sense the same results, that they are totally different than the remote opposite. But I didn't expect that. I expected that the collocated will give better results than the remote adjacent. Thank you.
Thanks for the question. Yeah, so I think, are you referring to this these graphs here where the remote opposite person has?
I say any result that you presented, clearly you can isolate two groups. One was collocated and remote adjacent. I am not saying that they were equal, but they were similar, and they were totally different than the remote opposite. But I expected, before you began your presentation, that the remote adjacent should be in some sense midway between the collocated and the remote opposite, and it didn't happen. And my question is, have you considered or analyzed the results, and have you any explanation for that?
Yeah, in terms of the gaze likelihood here and also the glance frequency, I think this is really just an artifact of how the participants were positioned, because they were positioned on this kind of virtual square, if you like, and when they were talking as a group, they were mostly looking towards the center. I'd also say that we didn't have gaze tracking, we had just head orientation tracking, so it's not particularly precise, and at times there may have been errors about which gaze angle is classified as which gaze target, if you see what I mean. So I think both of those things would play together and basically weight the results for the remote opposite participant a lot higher than they should be, which is what we see here. But yeah, at the same time, I think people probably would, by default, look at the person who is directly opposite them more than the people who are to one side.
Thank you, Gareth. More questions, Dietmar?
Thank you. Thank you very much for your presentation. This seems a very solid study here. And I was wondering about the context of this in comparison to some kind of ground truth, or let's say an anchor. How about, can you comment on the question, how does the performance of this problem-solving task relate to the situation where you do not have the setting that you're investigating, but a baseline? The baseline would be like a teleconference, like what we're doing here in the meeting, just to have like a Zoom environment, or even one step back, just to people in the same room. So of course that would be kind of like cheating, because this is for remote participation. So maybe you can comment on this. How far is this technology? How close is it to the baseline or an anchor?
Yeah, thank you for the question. I think there are. I mean, when I showed this image of the avatar quality, I think it's quite clear that it's not. It's not perfect by any means. There are visual artifacts, so it's clear that it's not fully realistic. But I think in terms of conveying movements, such as facial expressions and hand movements and all this, it's pretty close to real life. With our scenario, we won't see the person's eyes because of the shutter glasses which are worn. So in that sense, you don't get you don't get the gaze direction. You don't know where the other people are looking precisely, although you can tell a little bit from the head position, of course. So yeah, in general, I think it's quite close to a real face-to-face scenario. I think because of the directional cues that the avatar can give, it would perform better than a video conferencing scenario. Although, of course, one would have to really test this to make any statements about this. I would say that we would have liked to have done a real face-to-face baseline, but unfortunately the two locations of the screens were about 2 kilometers apart and it just wasn't really practical. So that's why we didn't do that particular face-to-face reference.
Thank you,
Thanks.
Gareth. More questions? One more, maybe? We have one in the... Alex, please.
Yeah, I just wanted to comment, although that's a really kind of qualitative statement, introspective. When we tested an earlier version of this, it was quite intriguing that we kept forgetting that one person wasn't wearing the headphone, right? So we were basically chatting as if we were all in the same room and kept forgetting that one person wouldn't be hearing what another person in another room was saying, right? And I think we really didn't have the impression in that case, or very much the impression that that remote person was actually excluded, but it was more actually the other kind of collocated person who didn't wear the headphone who was included, right? Of course, that's very qualitative, but I really think it is quite close to a real life interaction, really.
Thank you, Alex. Are more questions for Gareth? If not, let's thank the author for the presentation.
Thank you.
And let's move to the next one. I think it's Anton there.
Yeah.
Also
Can you hear me?
remotely. Yes.
Okay, so might take a moment for my webcam.
No
Oh,
problem.
okay, perfect. Okay,
Hello.
I see you can see me. Then I will share my screen. So, as my colleague Gareth Randall already introduced, I will talk a bit about the system that we used to record the study and also to analyze it. And this presentation, I hope you can see it, was
Yes.
done in collaboration again with Bauhaus University Weimar, TU Ilmenau, and University of Surrey, and my colleagues Gareth Randall, Felix Immer, Annika Neithardt, Karl-Heinz Brandenburg, Alexander Rake, and Bernd Fröhlich, and has the title Immersive Study Analyzer, Collaborative Immersive Analysis of Recorded Social VR Studies. And I guess the main question is, why should we care about it? And my presentation will be a bit different because it's more about the presentation of a system in that sense. So why should we care about recordings and immersive analysis of studies? When we conduct studies, we often are interested in certain behavior, such as the hand movements of participants, for example, because there might be behavioral differences between conditions. When we do analyze this data afterwards, however, as in the study here that we recorded with our system, just looking at the data during analysis, we might find some outliers that might be confounding for us. At this point in the analysis, however, it might actually be too late to go back and to see what caused these outliers. Are they expected behavior, unexpected behavior, technical difficulties? So the main question arises, how can recordings help us here? And in this context, immersive recordings that capture transformation data, audio data, state data, and additional data such as physiological data can help us during the analysis and investigation. Here we can see a study that we recorded with our system. And we can see that the participant is trying to select a shape on a box. However, he does have some troubles and he's waving his hand around quite frequently. So in our example where we analyzed the hand movement data, an outlier might actually be caused by technical difficulties rather than actual behavioral changes caused by the condition. Immersive recordings have the advantage that we can analyze them afterwards in virtual reality or on desktop PCs as well from any point of view. Here we have an analyst inspecting the behavior in closer detail. The immersive study analyzer that I will present today is an extension of that allows for recording of social VR studies. So here we have two participants, Bob and Adam, that have been recorded, and the analysis of two in a collaborative manner. So here we have two analysts, analyst A and analyst B. In this example, Bob is currently doing a short, small gesture, which analyst B in this case observed, but analyst A actually did not observe from his point of view. Through spatial and temporal navigation, both analysts can revisit this point in time in order to discuss and annotate the behavior collaboratively, which we can see here. In order to support behavioral coding, which is an essential part of in-depth behavioral analysis, annotations can be created for objects or as global annotations and are shared on a timeline between analysts. They can be navigated to temporally and be deleted as well. Outlines around the objects that have been annotated indicate created annotations that are currently active. During analysis, analysts are not restricted to watch the recording at the same point in time, as this has been shown to restrict and limit collaboration, meaning they can navigate independently in time and rejoin again afterwards, which we just saw here. In order to get a broad understanding of movements of participants, trajectories can be created through the timeline, through the UI for specified time intervals and are again shared between analysts. We can see an example here where we first view the trajectory of the head of a participant and afterwards of his hand. On trajectories, spheres indicate the point in time when the object was at this current position, as we can see here. Deletion can again be used. However, this does not really help us a lot because this just means manual inspection. To support exploration, our systems provides a set of analysis queries that can be created in virtual reality and analyzed there as well. Here we create a distance analysis query analyzing when the hand of the participant was close to his head. We can see the results on a timeline processed in real life and can jump to this point in time. Here we can see that participant Alice, for example, was actually quite frequently adjusting her HMD that she was wearing. So in our example with the recorded movement data, maybe outliers might also be explained by just a not very well-fitting HMD. However, in our studies, audio investigation was always important. In general, in our virtual scenes, we always have a lot of different audio sources. Our system records all of them individually, and in addition records the microphone audio of participants, as well as the audio that they heard after it was spatialized and sent through the network. All of this we record locally for each participant. In general, immersive recordings can be created for each participant, synchronized to a global timestamp. Through this recorded in and output, we can play back the recorded local state as it was experienced by the participants, but we can also respatialize individual audio sources afterwards in order to explore different spatialization modes in a realistic environment. And we can contrast both modes as well. Our system provides a set of base query types that can be easily extended, such as gaze analysis, audio analysis, velocity analysis, distance analysis, and rotation analysis. However, this alone does not help us a lot, but through combination comes power, and in this case, we can combine our queries as well as their logical expressions. So we can analyze when is user A talking, or when is user A looking at user B, but we can also analyze when is user A talking and not looking at user B. This might be a hint, for example, when visual communication might actually not be required to solve a task in an environment. We can see such a query combination being created here, where we first analyze when participant Alice is talking, afterwards create a query analyzing when participant Alice is looking towards the head of participant Bob. Here we just specify some parameters. And afterwards, we create a query analyzing when participant Alice is talking while looking at participant Bob. Again, results are shown on the timeline. In order to not only do this in an immersive way, we also allow for query specification using C++. In general, our system uses a plugin written in C++ as a backend. And this allows also for the analysis of multiple recordings, such as created by a study, in such a way that we can specify analysis requests individually, such as when is user 1 talking, when is user 2 talking, and then create queries in a logical, in a simple manner, such as when is user 1 talking as a single query, when is user 2 talking, when is user 1 and user 2 talking, when is user 1 or user 2 talking, and last but not least, when is user 1 talking, while user 2 is not talking. All of this can then be analyzed for all recordings that we have created. And this case of analysis, in addition to the immersive analysis we used in the study analysis for a study from my colleague Felix and the study just presented by my colleague Gary. For collaborative analysis, as already shown, we have shared annotations on a timeline as well as query results, a voice chat, gestures, and raise. However, as mentioned as well earlier, we also allow that analysts can navigate independently in time. This can result in situations where analysts don't have a shared common context. However, as a collaboration often requires to know what the other person is talking about, we need to facilitate this as well in our system. However, navigation to the point in time of a partner can be very inconvenient. Because of this, we establish a time portal, which allows us to see into the scene as currently experienced by the other partner. We can see an example here where analyst B is indicating where participant Alice is currently located at his point in time. The system itself is an open source Unity implementation and runs on Windows or standalone on Android, meaning the MetaQuest 3, for example. In the backend, it uses a C++ plugin for recording, playback, and analysis that also supports generic data. We have used it to record things such as physiological data, latency, skin conductance, or eye tracking information. And this can be used in theory independently of the engine, so it should work for Unreal, although there is no implemented support for it yet, and it runs on Android and Windows as mentioned earlier. To evaluate our system, we chose an expert evaluation presenting experts with two versions of our system, a base version with a focus on annotation and coding, as well as cross-temporal collaboration, and an advanced version with a focus on query and trajectory analysis. We had 8 experts from academia from different domains such as HCI and VR research test our system that were not involved in the design and implementation of it. We showed them a real-world study recording that we created with our system and asked them to annotate certain behavior and explore the recording using our tool set. This whole process took 90 to 120 minutes and was later analyzed in a thematic way. All 8 experts considered the capabilities of our system useful, and 7 of them mentioned that they could frequently envision frequent usage. The export of results outside of VR was mentioned as important. Use cases were mentioned such as in-depth behavior and conversation analysis, usability investigation, machine learning training data creation, and for coding, bias reduction, and training. The collaborative support of our system was confirmed by all 8 experts. During their analysis, we observed phases of loose and tight collaboration, meaning that analysts worked independently and collaboratively and navigated towards each other in time and space to discuss the task and discuss annotated behavior. The time portal was mentioned to be not easy to understand by one expert. And in addition, it was mentioned that when analysts are at different points in time, audio playback can actually interfere with collaboration because they not always know whether the other person is currently listening to conversation. A time portal adaptation was proposed by one expert where the time portal was mentioned to actually could show that it could show the field of view and the scene as currently experienced by the other partner. In conclusion, our system supports collaborative analysis of social VR studies. It has a coding and query-based analysis capabilities, supports tight and loose collaboration, and an expert review confirmed its usability and utility. For future work, we plan to explore how nodes can facilitate asynchronous collaborative analysis, how immersive recordings can be easily compared in order to identify differences, how queries can be analyzed for multiple recordings in virtual reality, meaning the navigation of such recordings based on query results, as well as support the development of our tool further as using help from the community. With that, thank you for your attention. And if you're interested in our system, feel free to check it out. It's out there and open source on GitHub. Thank you.
Thank you, Anton. Questions for Anton? Pablo.
Yeah, this is Pablo from Nokia. Thanks for the great presentation. I was taking some seconds to take a picture on the link. I'm very interested on,
No
on
worries.
having a look at that.
Feel free to reach out anytime.
Yeah, thank you. So I'd like to understand a bit what's in the plugin or in the system, right? So if, let's say, if I already have a scene which I do myself or whatever stuff, can I plug in your system as well, or do I need to build the whole thing using this, gray curtain thing that you are showing? So how is it? How would the integration look like?
So it obviously does depend on the system that you have, in the sense that if you're using Unity, we already have a pretty simple to set up system for that.
Yeah, thank you. So sorry, yeah, assuming, excuse me, yeah, sorry, assuming I'm using Unity in Windows or Android, yeah.
Okay. So assuming you're using Unity, then integrating the recording and playback functionality is quite simple, because essentially it is independent of the multi-user VR framework that we have used and that is present in this system here. The only thing that one would have to adapt if they would want to use their own multi-user VR system is the UI, in the sense that at the moment it is based on Photon for networking between analysts. And depending on the system that you're using, if you have netcode or mirror, it might be necessary for the collaborative part of it to adapt this. The multi-user VR framework, however, that we've used is otherwise not closely tied to the system itself. So it should be fairly easy to integrate, although fairly easy is always a big statement, not knowing the requirements.
Thank you. Great work, by the way. Thank you very much.
Thank you.
Thank you. More questions? Any questions from Zoom? No more questions. Thank you, Anton. We will move to the next presentation. I think it's Camille. So it is entitled VR Games Based on Circumplex Model of Group Tasks for Quality of Experience Measurements and Beyond.
Is it working? Yeah, okay. So my name is Kamil Koniuch.
And my name is Norbert Bartuk.
Yeah, and today we will present VR games based on a circumplex model of group task. It's model done by MacGraph. And I will be presenting the theoretical part, and Norbert will be presenting the technical part. This is the project that we did with Mateusz Olszewski in our team, and also Lucian Janowski. So yeah, a bit of story, and yeah, we will be presenting today the system itself and the small pretest that we end up doing just before the VQEG, and actually some part of this experiment are going right now in our lab. So this is really fresh. So about the development of this idea and of this game, so we joined the IMG project 2 years ago, and we were starting to work on survival game that was presented before. And what we found, it was quite hard to, well, similarly, to control the time of this task. So we were thinking about how to make this task better. And Lucian proposed some sorting task, and we found lots of problems with this task. So we changed it too. So we have lots of iteration of different tasks. We were trying to test them without the technology and also within the VR system. And yeah, this presentation is the fruit of these trials. So after many of failures with different tasks, we wrote down requirements and starts from requirements. So what we needed from those tasks, we needed they to be comparable, have some theoretical backgrounds, and mimicking different group processes. So instead of focusing on applications or like specific apps, we were thinking more about different group processes. And the goal of this is to verify if the type of task is actually influential on quality scores, and having scores or potentially in future metrics that depends on task, not on the system, which yeah, ideally would be more generalizable. So we use the MacGraph circumplex model. You might have seen it before. Different axes are like spectrums. So this is how different group tasks different from each other. So for example, there are more tasks that are more about generating things. For example, survival task is such a thing where you generate the ideas, or you have more negotiable task. And using this model, we pre-tested 3 tasks. So we design intellectual task, cognitive conflict task, and planning task. And we did it in a way that we start from really simple intellectual task, then we add cognitive conflict to it, and then we add planning that is necessary to go with it. And this will be presented today with the pre-test results. But in general, we have ideas for more of these tasks. So also for performance and competitive, and Norbert will also present it. So yeah.
Okay, so the system was prepared in Unity. We used HP Reverb G2 headsets to gather biometrical data like eye movement or heart rate. But the simulator is based on OpenXR, so it can also be used with Oculus Quest too. And we, despite from the biometrical data like eye movement or heart rate, we can also collect headset and controller's movement to analyze how users behave in our system. And we used Unity netcode to manage multiplayer capabilities. The first task is code intellectual task. It's a kind of interactive task where players have simple cubes with each cube contains a letter. And first player have an encoded word. We can see it on the orange board on the right. And the second player have encoding pairs, pairs of letters which need to be swapped. And if a letter is not contained in this list, then this letter remains the same. So the goal was to make a cooperative task where users need to communicate what is the encoded word, what are the letters to be swapped, and then they insert the correct cubes to the basket on the left. You can see. The second task is a cognitive conflict task. We call it visual conflict. We have similar cubes, but now one player see only numbers on these cubes, and the other player see only letters. And they both receive a hint. One player receives a letter, another player receives a number, and they need to communicate which cube is correct. In other words, which cube contains correct letter and number. And then we have a planning task, which is a different version of visual conflict task. Now users have a limited number of interaction with cubes. So they need to plan their strategy, how to find the best performance to share the information about cubes. Another task is a performance task. It is also a version of visual conflict, but now users have unlimited numbers of interaction, but they are limited to in time. So they need to, we wanted to analyze how people behave, how our system behave, and how it impacts the quality in a task where users need to be in hurry or need to work under pressure. Another task is a battle task. It's part of the competitive task. Now users, it's similar to the first task, but now there is no encoding part. Users just receive a sequence of letters, and there are 16 unique cubes with letters on it spawned, and users have two different boxes, blue and red, and each user needs to insert correct cubes according to the received sequence, yes, and they insert cubes and try to battle about these cubes. Okay. We wanted to make this system customizable for researchers' own research. That's why we support two different languages. We use Polish and English. We also use GC for voice communication, and other researchers can use their own voice servers. We can also configure network delays. We used Clumsy to simulate network delay on Unity interactions. We can use training mode to make players more familiar with system. We decided to make the training mode because in our pretest we found out that the users mostly doesn't know what they need to write. We want them to rate the system quality, overall system quality. And each task is customizable. And we can, for example, select for performance task, we can select the amount of time. For planning task where the interaction was limited, we can select how many clicks, how many grabs are allowed for users. And we evaluated 3 tasks. The first intellective task, visual conflict task, and visual conflict with limited numbers of interactions. We call them code intellectual, visual conflict, and planning task. And here are the results of our analysis. We made this evaluation on 14 users. We had 7 pairs, and we analyzed how they feel the quality of our system in 0, 300 to 1,500 milliseconds delay by which step of 300 milliseconds. And what I want to add is that we simulated the delay on a server, so it's more likely like video conference delay, where we are connected to external server, and we have a delay on our way to a server. Okay.
Yeah, so you've seen results from 3 tasks. We are planning to do 5 of them, and at the end, all of them. And all of those tasks that you've seen are quite based on conversations. So those differences are not so big, yeah. But we've seen with more people in our lab, we will see how big these differences will be. But when we have performance task or competitive task, then you have to actually be fast, for example, or have to compete with other person. And I would expect that with those tasks, we will see bigger differences. So yeah, summary is that we use MAGRaph model for task developments, and we hope that this will bring us better generalizations. For example, if you know that in your system there will be more like conversational tasks, you can see how, for example, delay influence those this system. But if you have more competitive applicants of your applications, then, for example, you will have the curve that it's a bit different. And yeah, our goal here is to actually test all of this MAGRaph model tasks. So if you want to join, this application is open and we can share it. And we would love to see more results from other labs. And yeah, from this pretest, conversational tasks are not probably that different at the end of the day, but I would expect bigger differences with the rest of the model. So that's it. Thank you. So are there any questions? Yeah, Pablo.
Yeah, I have 2. One is how many people there were in the
14. So we have 7 pairs. Yeah, so it's really early stage.
Yeah. No, I'm thinking about the confidence.
Yeah, they are huge right now. Yeah.
Okay, fine. And why the intellectual one is not so, I mean, deals so well with latency? Is that they don't need to speak too much to the other?
Yeah, basically yes, because it's we design it to be like as close to handshake. Yeah, so it's like it should be B. I have B, okay, and I put this letter. So it's like really short conversation with really not that much informations to be exchanged. Yeah, but later on with tasks that are more complex, is this pair or this pair, or you have to plan it, you have more actually information to be sent, and then they have to actually talk to each other more.
Thanks.
One additional question on the Pablo's question. So in the protocol was that one person spoke, the other answered, the other spoke, the other answered. So they couldn't interrupt one to the other.
They could, but they didn't.
Okay.
It was like in practice, they rarely did it.
Thank you.
Thank you. Alex, please go ahead.
Yeah, thank you very much. Very interesting presentation. So as far as I understood, you only had delay as the degradation, right? And per trial, you probably randomized the you basically randomized probably the delay settings, I suppose, right? Or you had some block design or whatsoever. And then I see you nodding, so so far so good. So that means you, in principle, for each task you were, I mean, sorry for the wording, right? I don't get to a better one. You maybe also have been training a little bit the participants to learn that there was delay on the line, right? Or on the connection, right? I'm just wondering, because I really find this delay aspect to be a very interesting one. You know, we have been doing some research in the past on just the pure audio aspect of it, and also a little bit of audio visual stuff. But I find this, it's a bit of an elephant in the room, right? And you know, and if you basically guide people by, for example, basically pointing them with the combination of task and different trials with delay to the fact that there is delay in the room, right? I mean, the elephant in the room, so to speak, right? This invisible elephant basically becomes visible, right? I mean, in the communication, right? And so I think it would be quite interesting to consider how you could be doing maybe more some sort of one-shot approaches or so that you really are more targeting your different tasks, right? Rather than, okay, you have the different tasks, but ultimately, regardless of which task it is, people realize that there is that elephant in the room, right? You see my point, right? So I'm not sure what exactly the conclusion would be, but maybe you can adapt a little bit the procedure by not having every participant basically conduct all the delay settings or the like. Yeah, thank you. Very interesting.
Yeah, so in this setting, we have like really small training for each task to show how this task looks like. And it was basically 0 delay and 150 just to show them that they can expect some delay. So in this matter, we showed this elephant before the ratings. We did the pretest without that. And yeah, we have all 4 and 5s and basically no differences, because when we asked people what they were rating how they like our system, for example. So they didn't understand the task itself. They start to rate how they will interacting with each other, but not the system itself. So this small introduction we find quite useful. Also, Lucian right now did some small pretest with Margaret. And they have, it was only a showcase, and I was spoken with him like just 2 days before arrival here. And they didn't have time to have this introduction and to actually show people what would be the task with the delay. And then people were rating all different stuff, but not the QoE as we thought. Yeah. So it's quite a tricky task. Yeah.
Thank you, Camille. Patrick?
Yeah, maybe I was not following totally. So you did so far 3 tasks, right? Correct. Did you show as the performance are influencing by the task, or the task dependent on the quality? You have the figures, because I missed this part.
This one or this one? I'm not sure which figure you.
Evaluation results. This is what I want to see. The effect of task here.
Here.
Okay. So that's what we get. Okay. So how do you plan to analyze that?
You mean?
Yeah, because it's super, I would say, qualitative here. So
yeah, we treat it as one of independent variables, the task itself. Yeah.
Okay. Yeah.
So we would plan to like model it separately and see if there are differences.
Like ANOVA stuff, or
I was rather thinking about linear models other than ANOVA, but yeah.
Okay.
So maybe GeoZ or other analysis.
Why?
Why not? Like for now, this is just the display from like 14 players for 14 people. Yeah. So we will see when we have more people with simple visualization if there is any effect that actually would like to search for. Yeah.
And why did you select these 3 tasks as a first trial?
Because they were simple and they were conversational, and we start, I'm not sure why this echo. We started as some alternative for conversational task for survival game. Yeah. So we would like to have something that is close to survival game, but maybe with more control, for example.
Because intuitively, I would have selected very different tasks. There are some.
Yeah, but we like first hypothesis. Yeah, if you would like to see if there's any difference between conversational tasks, if there is no difference between conversational tasks, then maybe on our meetings there is no time, there is no pressure for discussing which task is better, because if it's about a conversation, it will give you us like quite similar results. Yeah, so that's why.
Okay, thank you.
Thank you, Camille. I have one short question. I know this is preliminary, but can you point out already some benefits of these tasks against the typical survival one, or even the modification that we had?
Yeah, from our perspective, you have much more control. So you can choose the difficulty of the task, the number of cubes, for example, the numbers of interaction that is allowed. And thanks to that, you can fine tune it to, make it more comparable and less dependent on human factors, because we had this problem in other conversational tasks that, well, for example, the time that you reach the agreement is really, really dependent on what people do you have in the lab. And here it's much more similar, or at least you have some tools to fine tune it. Yeah.
Probably the engagement also of the participants on the task, right?
Yeah.
Thank you. So if there are no more questions, we move to the next presentation. Thank you.
Actually, there was a question in the chat
sorry.
from Shirin.
Sorry.
Yeah, it says.
In the chat, I was wondering if you could read it.
Hi, Shirin. Maybe you can ask it directly to Camille.
Yeah, the question is that very interesting. Thank you, Camille. And the question is that I saw in one of the slides you showed the performance that you will measure also. My question is that for measuring the performance, you consider objective metrics or some other metrics like qualitative data?
Yeah, so what we are interested here is basically if the measurements of quality on ACR scale is influenced by task. Yeah, so this is the main goal. But we also in the study, we are recording behavioral data, and we might also try to see the differences on other scales. Yeah, so our main focus here was like to what extent the task is influencing what we have from the tests. But we might also look for like more holistic view for QE, and then of course we will look for the performance, because this system is also tracking like times that it's gets people to go to correct answer. It's also measuring numbers of interaction with cubes. So you actually can do with this data set do those analysis. Yeah. So probably in the future we would like to take a look on this.
Thank you.
Thank you, Camille. Let's move to the next presentation. I think Shuemei is online already.
Yes.
Hello, Shuemei. Can
Hello.
you share your slides?
Yes.
So the presentation is called Point Cloud Quality Assessment and Visual Saliency.
I cannot start sharing a while. Okay. Oh, yeah, now I can.
Now you can, yes.
Yes.
We are seeing the now, yeah. Can you?
Oh my God.
Now it's okay. You can go ahead.
Okay. Yeah, I can. Yeah. Okay. Good morning or good afternoon and good night, everyone. I'm Xue Mei, and I'm a PhD student from CWI and TU Delft. Today, I will introduce our work about comparison of visual silencing for dynamic point clouds under task-free and versus task-dependent. And before we dive into the comparison and the insights from our subjective study, let's review some work about silencing. For example, this is on text and 2D video and 3D mesh. So silencing represents the distinctiveness of regions in an image or video that are likely to capture human visual attention based on some low-level features like the color intensity or high-level semantic information like the face. And in our work, we provide visual silencing data set for dynamic point cloud under task-free scenario, and we provide some qualitative and quantitative analysis to investigate the task impact for the visual silencing. And then we proposed a objective algorithm to measure the similarity of the point cloud silencing maps, which we modify a little bit the Earth mover distance. And actually, there are already quite a few visual silencing data sets for dynamic point clouds. But we identify one challenge is that those data sets, they are like created under different tasks. For example, visual search or memorize or quality assessment, or like a task-free, just to as lateral as you would. And also the generate the visual silencer map with different methods. For example, some people use truncated cone sector to map the gaze data to the 3D point cloud. Some people use like a log polar transformation. And by following the principle, like investigate one problem at a time. So in our study, we create a data set with the same method to generate the visual silence map, but under task-free dependent and task-dependent. So we have like two different silence maps. Task-dependent, where the user will do the perceptual quality assessment of the point cloud, and the task-free user just view the point cloud content as free as they want. And that comes the problem, like how we can say those visual silence maps, they are similar to each other. Although we can just like visually compare them, but I think objective matrix to is necessary to measure them. And the other question is like how the task impact the distribution of the silencing map. So the first thing we do is like we create a data set. And here we select 19 data set, 19 point cloud contents from two data sets. One is the UVG VPC and the other is the QAVA DPC. And this data set include like 5 contents, which we collected the task-dependent visual silence map on the data set from HI, etc. And the UVG VPC is a data set from Temple University, and they also have like the high quality point cloud, and they don't have copyright issue. So we can release all those data related to the visual silencing. And here is like the spatial information and the temporal information of the lighting contents. And then it's our experiment design. So basically in the task dependent scenario, we have like 4 steps. The first one is the calibration, because we do everything with dynamic point cloud in 6 degrees of freedom. People wear the head-mounted display. We use HTC Vive Pro Eye with eye tracking. So we have to do calibration at the beginning, and then inspection of the point clouds and rating the quality of the point cloud. And then it's the error profiling. The error profiling process, it's because the eye tracking technology in VR, we have to measure how reliable is those gaze data. So here is the short video, like show how exactly people did the experiment. So now he is doing the calibration, which is a 5-dot calibration provided by the device itself, HTC Vive Pro Eye. And after the calibration is successful, the user can go into the next step, watching the point cloud and evaluating. And each point cloud sequence is not 10 seconds and will repeat 3 times, just to give the user enough time to familiar with the content, and we have enough data to get the visual silencing. And now the people will do the evaluating. So it's like poor or fair. I think it's fair. And after the evaluating, the user need to do the error profiling, which we create this scene to measure like how reliable those gaze data. And we do this for every content. And after this step, the people can switch to the next point cloud. Yeah, but here you remember, so this is our task dependent scenario. And our task-free scenario is quite easy. We just remove the rating task. So by this way, we can collect in like 2 different visual silence map with the same method. And for how exactly we create the visual silence map, there are like 4 steps. So we have to verify the validity of the gaze data, and then we use a visuality-based method to identify the fixations in those gaze data, and then we map the 3D gaze to the 3D point cloud, and then we for the multiple users gaze data to one point cloud frame. And here it's the visualization of the final generated visual silence map. And then it's like our experiment results. I will like introduce from 4 perspectives. So the first one is the analysis of the movements on the physical space. And then here you can see it's like the movement on the physical space, the heat map, and the red dot is the content, the point cloud itself. For example, Rafa didn't move a lot, just cross his hands, and the participants just walk around and didn't have a specific location. And for Chaos Spin and Holland Goodbye, the move a lot, and people tend to stand at a specific spot to view this point cloud. That's something that we found. Of course, we generated the silence map for each frame. So that's the video visualization. And we also analyze the questionnaire from like the SSQ and IPQ because we are in a immersive environment. And here is the semantic analysis from the interview. So after the experiment, we interview each person by our designed 5 questions, and we label those same, and we can get some insights, for example, from the artifact and detail, temporal information, geometry and texture, etc. And then it's our important part, like the comparison between the task-free and task-dependent. And I will compare from two different perspectives. The first one is the consistency of the gaze. So here, the blue color, it's a task-dependent, and the orange one, it's task-free. And you can see that from the fixation, the volume of interest, and the spread of distribution. In task-free dependent, the participants will have more of gaze data compared in task-free. And that's because in task-dependent scenario, we ask the participants to evaluate the quality of the point cloud. So people need to be focused and need more cues to evaluate the quality. However, dancer is kind of an exception because dancer is a high movement content. So it's always moving and always attract people's attention. And then we compare like the consistency from the generated visual silence map. So the first one, there are already many metrics about compare the similarity of two visual silence map for image. For example, AUS until like the most familiar one, Pearson correlation. And why we choose the Earth mover distance? That's because we are compare the visual silence map of point cloud. And imagine if your focus or the silent area just shift a little bit. And in those metrics didn't consider the spatial distance, it will give you a large difference number. But with this Earth mover distance, it compares like the distribution of one silence map to another silence map. So that can be a more reliable measurement. And then we also visualize with like the EMD score and the PCC score for the file content under two different scenarios. So you can see that the score are quite low. For example, they are like no more than 0.5, and which means like the two different visual silence map under two different scenario, they are really quite different, which means like the task did impact the distribution of the visual silence map. And we observe the same trend for the other four contents. And a little bit summary for this, it's like a way calculate the maximum score for EMD and PCC. So the maximum similarity score. And apparently EMD algorithm consider frame 58 as the most similar frame, while PCC algorithm consider frame 61 as the most similar one. Maybe it's not obvious on the front view, but at the back view, we can see that frame 58, there are some like overlapping, but on frame 61, in task-free scenario, there are some silent area, while in task-dependent scenario, there is none, which means like the EMD algorithm can get more a more reliable result, more aligned with people's judgment. And the take-home message from those two experiments, the first one is the motion and meaning matter. So no matter it's on task-free or task-dependent scenario, the flow of the movement and the semantic information like the face they always attract people's attention. And the task do shapes the perception. They can affect how the signancy is distributed. And the third one is like we're just at the beginning to understand like how to measure the similarity of like two point cloud visual silence map. And there is no standardized way to collect the silence map. For example, when we map in the 3D gaze data to a 3D point cloud, there are like many technical problems. For example, the occultation. If some area blocking the another area, when you using the algorithm, we need to like distinguish this area. And the last one, it's like we need to engage with our participants, because sometimes we may think of, okay, the gradient or some like handcraft feature is quite important, but by the interview process, we can just ask their opinion, and based on our participants' feedback, we can get some insights from them. So basically, we released a data set. We provide our analysis, both quantitative and quantitatively, and we have our algorithm to measure the similarity of the visual silence map for point cloud. Yes, that's all. Thank you.
Thank you, Shueme. Questions? Yes. Patrick?
More than question, it's a few comments. First of all, or maybe it's a question. I didn't get pretty well the comparison that you were doing at the end, because, and that's something we did together with Resus. We have this concept of inter-observer congruency. So when you measure saliency, you may have a strong agreement between observers. That means one region will be salient for everybody. So you have really in focus region that attract all the gaze of your user. And as opposite, you have something like more exploratory content, and then for which you have less consensus between observers. So this has been well studied in the visual attention community, and it refers to the so-called IOC, inter-observer congruency. So I was wondering, are you aware about this?
The IOC?
Inter-observer congruency. And there are few measures of that. There are even some, I would say, deep learning model that try to predict this. So given a certain image or video, you will measure it will try to predict, similarly to predict the quality of an image, the IOC, how people will tend to look at the same part of an image or
okay.
Yeah.
So you are saying like there are some deep learning models that can predict the silent area of the image?
No. Of course, there is this, but it's more about the inter-observer congruency. Yeah, agreement. Okay, so that's something you can get either from measurement, like what you did. So from your measurement, in addition to AUC and all these type of factors that you get, you could include IOC measurement. So it's a measurement of inter-observer congruency. And I was just saying that even there are some works that people try to predict that. So similarly, that for quality, we have mean opinion score, then you can try to predict the mean opinion score. So IOC is one thing you should look at. Okay. Second, when it comes to graphical content, we have also one measurement, which is known as the visual attention complexity, VAC. That measures the visual attention, which is some are combining all this IOC stuff, but combining the things from different face or viewpoint of a 3D graphical object, or could be a point cloud, a mesh, whatever. So it's an objective measurement that try to measure the visual attention complexity of 3D graphical object. VAC. You can have a look on the work of Mona Abid, notably, where there is this type of thing. So I would strongly suggest to do that. And I have one quick question for you, because I could not see the interactive things here with the point cloud. It seems that everything is pretty well controlled. So I'm not. There is no interaction. So
there is interaction. You mean when I do the subjective study?
Yeah.
There is like basically, so people just move around. It's free. It's like a 6 degrees of freedom. But people just observe the content. You cannot work into the point cloud there is like what kind of interaction? Yeah.
Yeah. So the thing is that when you aggregate all the data from different users here, you have different, let's say, interaction trajectory. So this may affect also the inter-observer congruency. Yeah, because you have so many viewpoints, right? From one observer to another one, that like you did here. So I think it's also something kind of interesting to let's say characterize different point cloud with respect to the inter-observer congruency in terms of how you interact with the point cloud itself. Okay. So this could be a kind of extension of a 6DOF of IOC. So I would strongly suggest to include that.
Okay, thank you. Okay.
Thank you. I think it's time to leave, right? More questions? There are no more questions. So thanks, Shueme. I think we have to move to lunch.
Okay, thank you to all the presenters. Lunch break. So just congregate around Meta employees and let's start working. I suggest for today, we can stop the recording and we're going to